Okay, so I'm a PhD researcher at the School of Mechanical Engineering, just across the road. John here is one of my supervisors, the co-supervisor, and I'm investigating swarm dynamics around asteroids. So at the moment we send really huge spacecraft to asteroids, and they can cost anywhere from $200 million US to $1 billion US for entire mission lifetime. And they can also take up to 2 decades to complete. Now, an annoying thing about the US in particular is that presidential terms never exceed 8 years. So you're looking at a bit of political instability. And there's a current proposed asteroid mission called the Asteroid Redirect mission that might fall through because we're looking at an election now. So it's a bit of an issue. So swarm spacecraft might be a possibility to get around having these larger spacecraft that visit asteroids. And today I'll be talking about the positioning of the swarm. So the thing about a swarm is that there are numerous arbitrarily large number of spacecraft, and pinpointing where each one is during an asteroid flyby is a big challenge. There aren't any anchor points like you'd find around Earth, so we've got this great network called GPS and GLONASS and a few others that help us position exactly where we exist in the Earth system, but that's not possible when we're in deep space. But one great thing about asteroids is that they perturb spacecraft, so they've got a gravitational field. And so the purpose of this paper and this presentation is exploring how you can use that perturbation to pinpoint exactly where different swarm members exist. So just a little bit of an overview here. I know some people like them, so I'll run through this quick. So I'll talk about what a robotic swarm is, and then look into what asteroid gravimetry has been researched using swarms. Just a word to that. So gravimetry is the study of the gravity field of an asteroid. So I'll be looking at just the bulk mass of the asteroid producing a point source gravity field, but there has been talk about using swarms to investigate more than that as well. But it is difficult, and maybe we'll get onto that later on. So looking at our swarm in particular and talking about the problem of localizing or positioning where each of these spacecraft is during flyby. And then the solution that we've looked at, which is using the shape of the Doppler shift, or essentially the velocity curve, and then using rules to down select where different spacecraft are located. So for this we've looked at, or we have used simulations. It's a time-based flyby, so and you can't work backwards from it. So having simulations is pretty much the only way to go, unfortunately. And some of the future work that we've got planned as well. Okay, so there have been a whole bunch of robotic swarms that have been produced worldwide. The one that I've got here is actually based or produced by Harvard. There's fantastic people there. I think this is a swarm of 1,000 kind of nanobots, or yeah, kilobots, so 1,000 bots, and they organize themselves into shapes. So I've seen them make things like starfish and an arrow pointing somewhere, and a few other things as well. So swarms are based upon bees or ants, and they produce swarms in nature. So ants look for food in certain ways, and they have these pheromones which give little signals to other ants and can help you determine places where food might exist. Bee swarms, we all know about the bee dance. Not all the bees see the dance though. So how do all the bees still know where to go? Well, the answer is swarm, we think, swarming. So it doesn't matter. So when bees travel somewhere, they travel in a large group when they're first looking for a place to find food. And only some of those bees know where they're going, but they can use peripherals, using their eyes and other senses, to find where the bees that know where they're going are traveling, and they organize around them. So it appears that the bees that know where they're going don't even need to be up the front. They can be anywhere within the swarm, and then they sense one another, again using simple interactions, and find where they need to go. And some of these behaviors are emergent, which means that we don't know, or we couldn't predict that they would occur because the rules are so simple, but when combined over a large scale, so a swarm scale, things happen and we just didn't realize they'd occur beforehand. So that shows the importance of simulation as well. Because without simulation, we can't progress these swarms forward and find out what's going to happen. And in nature, in our simulations and in our robots that we actually build, as in nature, we use small sensors to interact with one another and sort of send information between different units within the swarm. So this picture that I've got here, I can't claim credit for. It's done by another group that are looking into swarms around asteroids. They're based in Maryland, at Johns Hopkins University there, at a place called the Applied Physics Laboratory, which is a fantastic place. They were the guys that built the New Horizons mission that went to Pluto. So a whole bunch of smart people there. And actually, the main investigator of this swarm that they produced attended SGC last year. So that's how we got connected. So strange things happen like that, and another reason for anyone in this room to consider going to that. All right, so backstepping first though, there was a first generation of swarms to investigate asteroids, and studies were produced by both NASA and ESA. They weren't great studies, so they were more looking at what a number of spacecraft could do rather than using the swarm intelligence that we discussed on the previous slide. But yeah, they really laid the groundwork and put swarms in people's minds. I guess another thing that they did was make the spacecraft too complex. So one thing about swarms is that you can have very simple spacecraft, and you should have very simple systems working with each other to make a complex system. And they didn't really take that on. So each of the spacecraft in this first generation was a real spacecraft in its own right. And I mean, if you cut down the cost of a mission by 10, so going from $1 billion to 100 million, but then you've got 100 swarm spacecraft, you're looking at a $10 billion mission, which is unfeasible. So it didn't really work out. Both of these studies fell flat after a couple of years. But looking at the second generation, so the main thing that we're both doing is looking at gravity fields, so gravimetry of asteroids. As I said, both APL and us, UNSW, are looking into this. And we're using the more of the swarm dynamics. So we're looking at very simple spacecraft working together, cooperating to produce behaviors that I would argue are hard to predict, but others argue that it's a bit more simple than that, which is fine as well. There's still a lot of benefits. So just talking about some of the different strategies that we're using. So one of the great things about having two different institutions looking at the same problem is that we come up with different solutions. So APL were sponsored by a NASA NIAC grant, so they got a bit more cash than us, and they were able to progress a little bit faster. And they looked at the entire, or they thought they looked at the entire solution space and came up with having a large mothership spacecraft that kind of sits back from the asteroid, and it looks at the little swarm spacecraft that move past. And these swarm spacecraft essentially act as light reflectors from the sun. So the mothership sits on the sun side of these and just looks at the light changing direction as they progress past the asteroid. One significant drawback to this is that they need to use numerical analysis. But as they've got a large spacecraft, they can transmit a reasonable amount of data back to Earth, do the numerical simulations on ground, and discover what they need to know on Earth itself. And what we're suggesting is that maybe you should be able to determine what the asteroid mass is on each individual spacecraft, and then you can make decisions when you're passing by the asteroid, rather than needing to wait until you've transmitted data back to Earth and then transmit it back again. So one of the things about very small spacecraft is that there isn't much power to transmit vast amounts of data. But we're saying that's okay, you shouldn't need that amount, especially with swarm intelligence, because you should only need a very small amount of data, not replicating, but mimicking those interactions already available in swarms in nature. So just double checking that I've said everything here. So the important thing about our swarm is that we use radios, which we assume will already be placed into these small spacecraft, so short distance radios, only over a few hundred kilometers rather than a few hundreds of thousands. And these small radios communicate with one another, and from that you should be able to infer both range and also Doppler, giving you velocity. And there are a couple of challenges there that I'm sure people in the audience won't bring up, so please do later on. So our main ethos is trying to minimize the number of sensors required for gravimetry, so just using communications technology, which we assume will be required anyway. And it's only self-referential, so at the moment when we fly by asteroids and we estimate their mass, we have to reference where the asteroid is located. But we argue that just using the referencing between swarm agents themselves, you can, one, figure out where the agents are based relative to the asteroid, but also determine the asteroid mass just from those relative movements. One drawback from the solution that we've produced so far, and we've been in contact with the APL guys. They seem to think that we might be able to figure this out just by using these relative measurements again. So one drawback is that you need the relative velocity between the swarm and the asteroid beforehand. But that's a work in progress. We'll see if we can take out that measurement as well. And then it can be purely self-referential. And at the moment, given a whole bunch of conditions, each spacecraft just needs two others to make all the calculations that it needs. So as long as you know that prior velocity, you can work out everything else just using two buddies with certain rules in place. Okay, so these rules, I've actually laid them out here, which is great. So the three spacecraft used must initially align along along their x-axis. So, and I didn't put in coordinate system here. Okay, so I'll quickly try and get the coordinate system out. So we've got x-axis, which is distance from the asteroid outwards past their closest passing point to the spacecraft. And then we've got y-axis, which goes up from there, so straight up in line with these velocity lines here. And then we've got the z-axis, which comes out of the page there. So the three spacecraft in question must align along that x-axis before they, when they start performing their maneuvers. And we do assume that we can't deploy these perfectly to start off with. And we get around that by having a whole bunch of swarm members and then not aligning them, but placing them in using probability distributions, placing them extending from a central spacecraft. But then we need to be able to localize where they exist. So the hope is that we'll find two other spacecraft that are kind of in line enough to make the calculations work, and to find out which two within a swarm of an arbitrarily large number, say around 100 members, we need to be able to localize where they exist. And the reason we do that is that there are no anchor points to work off. So we can't use a GPS style solution, unfortunately. All right, so I might skip forward a slide just to explain what happens here. And we've got two arrows that have moved, unfortunately. I'm going to use this screen here to point out what's going on. So these two arrows are actually pointing in line and they show the direction of velocity. So unfortunately they're pointing up here, but they were meant to align here. And you start off with a circle, or almost a circle. And as you move towards the asteroid, the leading part of the circle and the trailing part of the circle, that's happened before in presentations, and the trailing part of the circle start to stretch out. And that's because the leading edge feels gravity first, so it moves forward faster. And the trailing edge feels gravity last, so it lags behind. And then the part in the middle kind of stays between those two bounds. But as it moves past further, they come back to where they were initially. So the circle in the direction of travel comes back to where it was. But because of the differential gravity, the sides start to move away, and they move away in a linear kind of fashion, or linear enough in these hyperbolic orbits. So the asymptotes of the velocity line up here, and then they're moving away from each other there. So from the change in the asymptotes and knowledge of the relative distance between the swarm members, we can figure out the mass of the asteroid. And in that way, we don't need to know how far away from the asteroid we are either, because there's a unique solution for 3 swarm members, or unique gravity curve, if you will. Okay, so what happens with all this sort of expanding and contracting that goes on is that we get velocity curves. And I've had a little bit of trouble with this diagram that I'm showing you guys here, so I do apologize. I'm working on it at the moment, hence the other diagram that I just showed you. But the contracting gives you, or the moving apart gives you a rise in the velocity relative, and then it just stays constant as it asymptotes away from the asteroid. And depending on where you are relative to the central or measuring spacecraft, you get a different curve. So is that working? Actually, yeah, so all of these curves are different. I'll just explain what this kind of wedge shape is. That's probably very confusing. So just in the middle here, if we assume that this is a sphere, in the middle here we've got a measuring spacecraft. And this is 3D, shown on a 2D diagram, so hence the confusion. But then we've got a circle on the same plane that extends around, so we've got y, xy, and x axes. And then this actually completes the sphere, so z is straight up from the measuring spacecraft. And so this diagram probably shows too much information to be easily readable, but each of these curves symbolizes the stretching and contracting that occurs around this from the centroid, so relative to measurements from the centroid spacecraft. And all of these curves are representative of the Doppler shift that you would see. And each of them looks different and is different mathematically. So we can use simple rules to interpret which of these curves that we're seeing, and therefore work backwards and figure out where each one sits relative to our central spacecraft. And I call it a unique signature. Yeah, I think I said everything I wanted to there. Okay, so please ask questions about that. I'm really trying to work on it. Any ideas how to represent it better in 2D would be very welcome as well. So just a quick point on rule selection. So if you were to just use a sphere to work out where everyone is, that's pretty easy to do because all those curves are different. But if you just use simple parameters to figure out which agent or which spacecraft is which, it doesn't really tell you what happens as you contract and expand the sphere. So these different parameters really change as you move away from the spacecraft as well. So there's another dimension to it again. And this graph that I've shown here is meant to be confusing. And I chose the most confusing graph I could. But it just shows how the parameters really change depending on how far away from the spacecraft that you have. So each of the lines that I've shown here represents one of those major axes that I pointed to in the previous diagram. And so trialing which of the parameters I could choose to really make good rules to pick between them was a little bit difficult, but after a lot of trial and error, I did distinguish that I could use only 3. So the bottom point there gives me the 3 rule names, which are K1, K2, K3, just to be really boring. But yeah, in conclusion, with 3 rules, I can work out where I can work out where my 2 other spacecraft are that I need to measure with. And this just gives a quick overview of how the logic works. So I called the first rule K1, looked at the direction of the final velocity, so it just saw whether after the swarm flew past the asteroid, whether the spacecraft were moving apart or moving together. Then shape ratio, just use a ratio between the maximum minimum velocities seen and also the final and starting velocities as well. The final rule was final velocity over distance. So I looked at what the distance was, or the range, between spacecraft to start off with. And then by dividing the final velocity by that original distance, you could pull apart the last few axes to see who was where. Okay, so with simulation I used a whole bunch of points, so 1,000 different spacecraft randomly distributed around the central spacecraft, and I just used a single asteroid just to make things easy. So it's also possible that these rules won't be effective for different asteroid sizes, and that's one of the things I'll be looking at in the coming months. So I looked at an asteroid that's about the size of 253 Matilda, which is around 50 kilometers across. And it's almost kind of spherical, more spherical than a lot of asteroids anyway. And this swarm was displaced from that asteroid by about 100 kilometers. And I used the normal distribution in 3 axes with a standard deviation of only 5 kilometers. So it was kind of a tightly packed swarm located about 100 kilometers away from the asteroid. And as they zoomed past, weird things happened that I was able to measure. So looking at 1,000 spacecraft, on average I got I returned 4.3 after applying those rules to get appropriate spacecraft that could be used to measure the mass of an asteroid. I've got a note here that I only actually needed 2, so 4.3 was additional to what was required. And so for this kind of configuration, I could use fewer swarm members in order to get a good solution still. Noting as well that in this simulation, I just used one of these spacecraft to make the measurements. So I could have picked any of the spacecraft that was simulated here to make the same measurements, but just for simplicity, I used one. So if you got an average, instead of 4.3, you got an average of only 1, then let's say you had 100 spacecraft instead, any one of those 100 spacecraft could be used, and one of them would have more than one fellow spacecraft that it could use to measure. So that would have been able to get or return a solution as well. So I had one rule, K2, which could be have modified sensitivity. So you get a worse result from modified sensitivity, but you get more, or you return more spacecraft that can produce good measurements, or a measurement, I should say. All right. So just talking about there being one case used. So there are a whole bunch of perturbations that you would see in the real world that I didn't simulate. They include solar gravity perturbation. and also solar pressure perturbation as well. They were just taken out for simplicity, and this is a technique that's often used by NASA just to get this kind of new research, or investigate using this new research, and then they figure out how to take out those things later on. Yeah. So one issue that I have is that with a hyperbolic trajectory, you can't actually use two-body curves in order to make an approximation, and that's because there's no time-dependent position on the curve that you can get. So you've got to use numerical techniques to find where everyone is at any one time anyway. So the best thing to do was to propagate forward using an orbital propagator that we've developed here at UNSW, and that produced a better, similar if not better solution than using just normal curves. That would probably also be the case for eccentric closed orbits, but not the same for circular orbits. But I mean, no real orbit's circular anyway, so it's better to simulate rather than use these analytic techniques. All right, so looking at a few things. So my K3 rule was pretty good on the ground, but I don't think it'd be quite effective in space, and that's because you need to match curves at the moment. So a little bit of work there would, I believe a little bit of work applied would make that effective actually. Yeah, so I only looked at one passing velocity as well, which was about 1 kilometer per second, which is realistic, but it'd be nice to get a few different passing velocities in there. And I'm investigating the limits of my computer at the moment, so I'm just using desktop. And actually with these simple kind of interactions, it's not too bad simulating using it. I know the parallel computing guys really want more people to work on their computers, but I don't think I need it in this particular case. And I think one of the benefits of the swarm, and one of the things we should try to do, is make the interaction simple enough that you don't need large computing power on Earth or in space to make it work. Anyway, thanks so much for listening, guys, and really happy to answer any questions. I see we've got one already from Sanad. Did you want to?
Yeah. Do you think that this method can be applied to non-uniform asteroids? Not very uniform, because you said that it's very spherical-ish.
Yeah, so at the start of this whole process, so 2 years ago, we thought that we could find a distribution of mass in asteroids, but going at these relative velocities, so in a hyperbolic orbit, we see negligible impact on the trajectory of the swarm. So because we linearize already, we'd probably linearize out those small perturbations anyway. And so, yeah, we can't really find it at these velocities. And we probably have to find another solution if we were to go slow enough to look into that.
So what is the distance between the asteroid and, say, centroid of the swarm you were expecting?
Yeah, so here
where this will be applied?
So at the moment I put in an aiming radius. So that's, if it was unperturbed, it would pass at about 100 kilometers from the center of the asteroid, or about 75 kilometers from the side of Matilda. But what happens is that they're perturbed ever so slightly, so they actually pass at maybe 98 or 99 kilometers, but it's still reasonably far away. And far away enough that you wouldn't see this perturbation, but also fast enough so you wouldn't see this perturbation. Or you would see it, but it would appear like noise in your results. So unfortunately not possible, but with slower flybys and maybe not a swarm technique, you'd be able to determine that for sure.
What if the asteroid had a beacon on it, so you were actually making absolute measurements rather than relative?
That'd be really cool, and I know we've discussed that before. That'd be awesome. Yeah, so I guess the trick is landing it, and then it would be a two-way system, right? So you'd have an absolute beacon, but then you would have to probably have multiple beacons, and then you would position those beacons using your swarm. So one would reference the other and then you'd figure out a solution. But yeah, that would be really great. And then you'd start to be able to do some of the more non-linear stuff, so very close operations as well.
About what speed is the flyby?
It's about 1 kilometer per second, which is similar to the original EROS flyby by, what was that mission called? The near Shoemaker mission. And yeah, a variety of flyby velocities have been used in the past, but whether you get good results depends on how large the asteroid is. So up to 10 kilometers per second relative velocity has been used, but that was for a huge asteroid called Lutetia, which was about 100 kilometers across. So the bigger asteroid, the more you can play with those numbers.
Early on in the piece, we were looking at irregular asteroids and doing orbits in the lab anyway.
Yeah.
Around then. How do you decide that that's not practical? I mean, it's obviously a flyby, but is that not practical as a way of finding the relative masses of the?
Yeah.
I know we can do it in the lab. I just wonder.
Yeah. In the lab we can do it, but I think using these simple interactions, it's not possible. So we need more information. And the other thing we've done is linearize equations. So we would start having to look at numerical techniques, which I believe wouldn't be well performed on a small spacecraft. So then you'd need to think about sending data back to Earth or to a larger spacecraft or something like that. So I wish we could though, because that feels like the whole point, right? So
The simulation is pretty.
yeah, no, the simulation is awesome. So yeah, please.
What's your guesstimate of the size of each installment?
Oh, how big that would be? So I assume it would be around 10 centimeters squared, so 1 U cube. But yeah, that is a guesstimate.
About a kilo's close.
Yeah, roughly, yeah.
Could you expand a little bit more on the 1,000 to 4.3 ratio? Like, how'd you get that?
Yeah, okay. So basically, I simulated 1,000 small members, and then I just used a normal distribution using standard deviation of 5 to put them on curves in 3 axes around my central spacecraft.
So it's more of a numerical method of calculating after a simulation, right? Like you simulated 1,000 swarms and then you...
Okay. All right. So interesting that you put that forward. It's not at all a numerical method. So it's a rule-based method of figuring out where everyone is. So I already have, so I've already simulated these curves, and then I've been looking at each individual curve to see how they're different to other curves. And so I use rules to differentiate between, not differentiate mathematically,
so you
differentiate.
make these certain rules so that you know you have, you're able to make a difference between the effectiveness of the velocity.
Can you please repeat
Like,
that?
have you made your own rules like K1, K2, K3
Yep.
so that you actually can figure out the relative velocity curves, and then you sort of use those to bring out the ratio?
So I use those rules to figure out who actually meets the criteria that I put forward. So there's a very limited criteria based on linearized equations that I've created as part of a previous study. It's very limited, unfortunately. But if you use 1,000 small members and you do have them distributed in the way that I've put, then you can get around 4.3 small members on average that meet those criteria. So you've got your centroid, then 4.3 other spacecraft. So obviously it would be 4 or 5 or less or more, but yeah. So that's what I mean there. So it's, I mean, I've produced the Doppler curve numerically. That's the only numerics involved here.
Just a question around, obviously, your alignment with the asteroid seems kind of critical. What's your planned delivery method, and how would it be different than just sending a big satellite there in the first place?
Yeah, that's a really good question. So this whole system's set up so you don't need the big spacecraft, but yeah, how do you deploy those spacecraft?
So is it going to be Voltron? Voltron that
Yeah, that's
splits,
right. So I think it would be really valuable to have these deployed very remotely, so hundreds of thousands of kilometers away. But then you've got non-linearity of the sun's gravity field affecting each individual swarm member. So they'd be unmatched by the time they get there, and then they'd kind of pass by in a string hundreds of kilometers apart, which would be totally useless. So to get around that though, it is possible, and this has been looked at before by some possibly smarter people than me, is that you can launch them so that by the time they get to their destination, they're configured in almost the right kind of, or like a bunched up swarm, for example. So it is possible to launch them in such a way that they would do that after a period of time, and I think that's an area that I'd really like to look at, but hopefully I get time. Otherwise I can just say that it magically rearranges in the right way when it gets there. Oh, so now another one.
Yeah. Are you looking at any specific region of space for applying this method? Because you were talking about two body only, so
Yeah, that's right.
what do you think the effect of other planets?
Yeah, probably not other planets, but definitely the solar orbit perturbation itself. So you're in a hyperbolic trajectory about the asteroid, but you're still in probably an eccentric orbit, closed orbit about the sun. So you get these epic non-linearity effects. One great thing is that the time scale about the asteroid is very small, but the time scale about the sun is very large. So you can start to linearize your trajectory about the sun as well. And I've done a bit of work to look at that. Nothing rigorous as yet, but it seems to be easy to just take out the sun's gravity. And so if you were to model it without the asteroid, it seems like I can just take out that model without having it affect the linearized orbit about the asteroid. So yeah, it's a problem, but it appears to be easy to solve.
Okay, so
To wrap up.
I guess for near Earth asteroids it would not be easy, but for deep space,
Yeah. Actually, I think because there are around 50 asteroids passing closer than the moon that we know of every year, and one or two of those are probably big enough to have their gravity determined using this technique. So I'd like to look into that because I think it'd be really cool.
But in that case, I think gravitational field from moon and Earth.
Yeah. Yeah, both of those, if you're in the Earth-Moon system, both of those would be relevant, and the sun as well. So you got four gravitating bodies that you're dealing with. So I guess the problem for me is that can you take those out in an easy fashion without having to use numeric? You don't think so? All right, I'm going to look into it and we'll find out. Yeah, you could be right there.
It has been 300 years for multivariate problem, but
oh, agreed. But
no solution.
Yeah, no. As I was saying before, all you need to do is have the flyby of the asteroid over a short enough period that you can treat the other bodies as one body, essentially.
I mean, to great purpose, you can use the Earth body alone to plot a satellite's trajectory quite accurately and ignore the moon's trajectory, because the moon's trajectory is so much slower than the satellite's trajectory around the Earth that basically you can reasonably well work out the orbit of the planet around the Earth, ignoring the moon, reasonably well.
The other thing to point out is that even if you're at the radius of the moon and the moon's on the other side of the Earth, then it's far enough away that it has almost no effect. So you can already discount one body almost, and then you've got to deal with the other two, so as well as the asteroids. So I think there are ways that you can cut it down, and you've really got to get that flyby going fast in order that you can really linearize what's going on. That looks like it. Thanks, everyone.